Welcome back, guys. So today, yesterday we went through the theory for what we wanted to achieve and what are the helpers we currently have implemented, like the Kernel, and also the high level or flow of what we wanted to see is that we want to see an user process that tries to allocate memory, and it goes through the syscall, and we do the context switching and stuff, and we implement the syscall handler, exception handler, plus we have our final kmalloc that's actually going to do the stuff. And now we're just gonna return the same thing back to kernel, back to the user space, and this is what we want to achieve. And this is exactly I was just blabbering about yesterday. Now it's time to actually get into the implementation. So, most of it is has been already developed, because if you have followed my previous blogs, I have already prepared a separate session where I implemented a kernel simple scheduler. This is just going to schedule multiple processes, and I have a separate session about kernel interrupts. That's just gonna handle several different types of interrupts. So we should be merging all these three into the single MMU, because we need interrupts and scheduling and the user level stuff, so we can bring it all together. So now let's keep this as our main thing, so we know what we want to do. Now let's start by bringing user process. So what exactly is an user process? In that case, we are inside kmain, and kmain is still in EL1. We're supposed to go into EL0, because user space is not supposed to be doing privileged operations. They have to do privileged operations through syscalls, and that's the whole point of separating kernel space and user space. So let's think about it. We are inside our kmain. Maybe we could remove this part because it'll be too hard to scroll around. We can press delete and maybe put it down somewhere. What the fuck happened? We could just put it here. And we have the main docs. It will be, let's say, to do. We can format it a little bit better. Okay, so we are inside kmain, and so we are still in EL1. So what can we do here? If we need a user process, that means we need task struct. Let me just give a small introduction of task struct, because I don't want to spend the entire time on top of it. Let's just check task struct. It's taking forever to load a page. What's going on? Is my internet slow? It's not slow. I mean, like, a general task struct will have lots of fields, but in general, it's supposed to have some main things. Like, it's supposed to have the linked list to the different tasks, because it might have to switch things. So we need to have a what's that? We have a linked list to some tasks, other tasks, And we need to have the context, because as you know, what exactly do we mean by a process? We just mean by the environment that is running on. So we as a CPU is just a state machine. So whatever is in the current interrupt point, or no, what's that, instruction pointer, and that's what is going to be executed with the context of the registers and the flags and probably the memory. So this is the key points. And to switch between processes, all we have to do is just keep track of these registers, save them, and replace it with the next processes registers. And so a context is just storing this information. I believe it should be somewhere here. Maybe, I don't know, but I believe it should be there. Maybe it's being mentioned as something else. We have flags and we have stack. Maybe state is the actual thing. State. If we go to state, it's a long, so it's not that. Okay. It must be here, because we need to keep track of that PCB, process control block. Or maybe PCBs are physical, maybe in a real kernel. One thing, how does task struct keep holds count PCB? Oh, struct task struct itself is the, yeah, I know that, but still within that we need to have some information, right? This is the state. So if we have multiple processes, we just switch them between these states. And this is what I mean by a process control block. It has to have the CPU registers and current scheduling information, as in whether it is running, whether it is being put on wait, or is it waiting for IO. But in our case, we could have just maybe 3 cases where it is ready for being executed, or it is executing, or it is waiting. So there's 3 states. Okay, so the entire task struct is the representation of things, but I still want to know where is the where within this task struct do we save the registers? We have scheduling information, that's time slice, state of the process, address space of the process. This is the context switch. Save the state into PCB, we switch, we execute something, save the state, reload previous. Those are fine. I just want to understand within task struct. I think it's no longer essential. Within task structs, where do we store the registers? Which fields? Oh, okay, so it's thread structs. This is what we want to. Let's check it. So task struct, data structure, and threads. Where's threads? THRET. Thread group. We have thread group. It's here, thread struct. Clicked on top of it. Let's see if it's low. He who. The website name is He Who. And it's taking forever. Probably Cloudflare went down. It's been a thing right now where Cloudflare just randomly fucks up all. Hopefully the stream is still going on. We could just Google it. That's far better. Thread struct. Kernel. Not this. Let's see. I think this is it. See, it has the S, but this is for some other OS, but probably running on top of Linux. So we have the TID thread status, that's current status, name of a thread, and pointer to a pointer to a stack. And we also have process. So PCB is on its own as a separate struct. Maybe this is some other kernel. Let's just think about the Linux kernel. It's he who won't load. It did load. Okay, let's see. He who. We have file name. Thread struct did not give us enough information. We have some functions, but it did not say this is why we should not just directly believe it. Yeah, but if we can see it inside the kernel, it would be more visual without having to go through our version of it. I mean, we do have our version. Let's see how our version looks. Must be simple. As context.h, and this is the context. We have 31 registers we have the special register, and we have the EL1, and we have the flags. And this is, I have defined it as a construct, and I've also aligned it so 16 bytes, so you can just directly take the pointer to it and do pointer arithmetic instead of messing up the structure. Let's go into schedule.h. This is my task, and task has an ID. Task state is can either be ready, running, and blocked. And I have the top of a kernel stack. Every task can have a kernel stack and a user level stack. And then I have the time slice that is left. Why did I keep it as just int? I don't know. And I have a name, and it's also going to be in linked list. So it's going to have a next task that is currently that got added to it. And let's see. Yeah, I guess because in my case context is everything, because context is going to have everything that you want. Nothing much. And other than that, what can we do? Let me just change this. Okay. Turn to look. Okay. And let's see. We have the context. It would be good if we could see it in the Linux actual thing. This is the one. We have the registers. Yep. We have the registers. This is the main thing. What is this name? The thread struct. Okay. This is what in Linux terms, the thread struct is the one that is gonna be having this whole information, and it's going to have a lot of stuff because it has stack pointers, some frames, some debugging information. It also has trap and the registers. What else do we see here? There has a lot of stuff which I don't know. But yeah. But I guess because it's a fully fleshed kernel, I think we need all of those stuff. But in our case, we're just going to have ID, a state, and the actual context. And here, in my case, because here we have task struct, and the task struct holds a thread, and so within Linux everything is a thread. Even if you have a process, it's actually just thread. It's just one thread that is being scheduled by the kernel scheduler. In my case, it would be everything is a task, and tasks have their own context, they have their stacks, and they have some names and stuff. It's almost the same. So now we could just copy things and paste it inside our current projects and hope to integrate them properly. Let's see, how can we do that? What am I supposed to do? I'm inside simple menu. Let's close this. Let's ls Kernel simple interrupts or scheduler. No, scheduler core probably. And we might need these into, let's just go into kernel simple MMU, and we have these things. Let's create core, and let's create we're gonna create I think we can create a separate scheduler directory, so it would be more organized. I don't know. Okay, we can have it in a separate one. Let's put schedule code and scheduler. Scheduler scheduler. I hope it's the right way to call it. Scheduler. Yes. scheduler. Yeah. Scheduler. Let's just copy. What do we need? Host. I guess it's in desktop. Kernel. Host kernel. Core. What's that? So kernel simple scheduler core. I need context here. And what do I need? I might need schedule.c, and I might need schedule.h. What else do we have there? We have timer.c, and as I mentioned yesterday, we definitely need timers because kernel is also going to be driven by timers, because we have multiple things that actually use a kernel, because like the event loop, or I guess even for packets we need some sort of clock. So yeah, we definitely need timer. Handlers, maybe we can write our handlers this time, because we have a different structure. Maybe it's better to write some things from the scratch and reuse the other stuff. Okay, we have the context.h, and we have the context. Oh, we didn't copy the actual context.c. I think maybe there's no context.c. Okay, I guess there's no context.c. Yeah, there is no. Okay, now let's try to update our k-main then. Let's create a task struct, which is this task in our case. Let's import context.h, and we can create tasks. There's no task in my context.c. Okay, there's no context.c. It's inside scheduler. sc. We are inside scheduler and context.h. Okay, now we should have the task. Still no? What the fuck? Oh, there's no task here. Where did I define task? Oh, it's in schedule.h. Okay. Schedule. Context.h and it's schedule.h. Task. Now we have to define multiple tasks, and then we have to schedule those tasks and keep start task as the starting task, and then it gets some time slice. After that it will be scheduled off, and we have the second task that will get some time slice, and it's gonna keep on continuing it's gonna drive each other out of to completion. So let's see. We need a task. I guess we might need to write a task. Initialize the init task, and what does it have to take? If we could open our main. Okay, we already have a task in it, and it takes a task struct. Here at that time I didn't have any heap or the actual stuff, so I had to do global allocation, but I think we don't need that anymore. We can allocate as much as space we want and do dynamic stuff. We have the camel lock. Also, one more thing is that it's better to not put the stack inside the because stack has to be in a special location, so we need to map a region as the entire process region for this task. So this task gets a full region. I mean, that's exactly what virtual memory is supposed to be doing. So in that case maybe we could just give it some in that case, from user space, every user space has a full virtual memory, and all we have to do is that whenever a user process tries to allocate something, we have to add mapping in our page tables and keep the virtual memory as it is. So maybe that's why a user space allocator is needed in this case. Do we have to go with that? But then it will take a lot of time to fix that up. Maybe we can add that in the second iteration instead of doing it now. I think we can do it later. I think we can stick to this approach where we assign things in the global thing, so we know that we have a stack, and I mean the user stack and the kernel stack that is completely assigned somewhere, and we won't overwrite it, because in case if I use my allocator right now and if the stack grows beyond that, what will happen? Mm, that's my current chain of thought, I suppose. But I don't know. I guess we can just directly use our Camelot instead of doing it this static way. Let's try. Let's try. Also, we don't need to take this as input. We'll allocate certain thing and we'll send it off. We could, what would be it is like we create void star task equal to kmalloc, and we pass size of task. That's it. Now we have a task struct, and id, we can take an id, we can take a name, and we need a actual function that we want to run. And we have kernel base and stack base. I think we'll allocate both the stuff ourselves. So in our task we are only going to be taking a pointer id, and we are also going to take a name, and we can take the actual thing to run, that is a void entry. Do we need function parameters? I think it can take one arguments, and it can be an array, so we can have multiple stuff, but then it's being started from kernel space. So how exactly can we create a function that can be used from... No, I'm losing the chain of thought. Actually, if we are inside the kernel user space, and user space has a shell, and shell will give access to that, so we don't have to worry about the shell. Will be the task that will be started by kernel, so user space can use this shell to do the rest of that. Yeah, so it's fine. So I don't think it has to take any arguments. You can just keep it as void, and we don't need the stack base and kernel's base, because that we're just going to use our kmalloc size t. Yes, that's okay. Let's see. I think we also have to... I think it's standard definition then. So it's standard definition. Okay. Too few arguments. Oh, it has to take allocate mem. That's annoying. Can we move our allocate mem to top of some global stuff? I think we can do that. We'll just move it to the top, and our main will actually initialize the bitmap, and it will add it to that. So that's fine. Now all we have to do is assign the task, set the main. Maybe just take pointer reference, and that should be it. We have a task. Now we need let's assign the same space, define stacks stk size. Maybe we'll put stack size, as he said, as 4096, and we can create two stacks. It would be uint 8 star k stack equal to kmalloc main, and we just put stack size, and we can do this again, and we put a user stack. So we can now dynamically allocate memory, because in previous example I didn't have that option. Only thing I could do is create global or allocate it as static values and use it. Now if my kmalloc works fucking fine, I should be able to do stuff like this, because they all lie in the heap. At least in my terms, it would be having the entire RAM access. So as long as the RAM is there, as long as the RAM is not filled, I think this whole thing will work. And right now I don't have any free. Do I have free? Okay, let's think about memory freeing later. Now let's just create the tasks, and we can finally just allocate stuff. It would be task id equal to id, and task name equals to name, and we have the task kernel stack, that would be k stack, and we have the task use stack, that would be our u stack, and we have the kernel k top. What is k top? What's k top? It's stack base plus SZ. What does that mean? No, I didn't understand. We take the base pointer plus size, that's the k top, and k top minus size of context. There's the context. I think we are allocating the context in the kernel stack, and we are using that pointer here. I think I did this because I don't have dynamic allocation. I cannot do dynamic allocation, that's why I guess I did this. Or maybe is it for process separation, because the context of the process should lie within the process. Is it even a thing? I'm not sure. Can we store the PCB outside of the process? Would it be in security vulnerability? As long as the mapping only is available within a process, we should never be able to read even if it is outside the context. Yeah, but I think this is what is happening here, because we just take the kernel stack's base, we add size to it, and then we take that location as the pointer to ktop. That's what I'm wondering. Why is it that we add that size and take that as the base pointer. No, as the kernel top. What is the size? Let's see. Stack size is just stack size. Oh, that would mean that like we are taking the base, we are adding the entire we're adding the entire size. So we are going to the end and we are taking that as the top. Why can't we just take the top as the top? Why do we have to go to the bottom and say that this is the top? Because heap has to grow, stack has to grow upwards. Is that why we are doing it? Let's see. We had some image here. Where did that go? Stack has to grow downwards. Then memory addresses will be growing upwards. Oh, maybe that's why we just go to the bottom and we point that as the top. So every time I guess stack we just reduce number, reduce the current things because we don't. Okay, probably that's why, because let's say stack has the last value here, last item, no, top item. When the next top item at, let's say, location 0, when you add the next item, you add on top of it new item, but you don't add 0 plus. I think we put 0 minus some constants, and this location will be the, because it grows downwards. I have no clue why I have added it, but this is one possible reasoning, because it has to grow downwards. We need to go to the end and then we can just keep going downwards until the end, and so we just keep subtracting to go downwards. I don't know, maybe we don't even have to implement it. We can just put it as a to do and see if something breaks, we can think about it. Because as you can see, we took the k top and we subtracted the amount of size and we took that as the context. So it's definitely possible that this is what is happening, but I'm not fucking sure, because maybe something else. Right now I have no way to tell what I did. Is that what I have implemented? But from the looks of it, it does look like that. Okay, what is build initial context? Okay, so we just pass that pointer. Now we just allocate values within this pointer. But because we are doing subtraction here, that definitely means we have to go to the end, because without going to the end, if we subtract from k base, we would be underflowing our stack, I guess, because if the stack size is here to here, instead of writing between these values, if this is the start and if we subtract, we would be going downwards. This is where we would be writing stuff, but we want to write it here. That's why we create one, and this is the initial start. So we add the entire path, so we reach here. So now we point here, so whenever we subtract things, we'll be writing stuff within it. I believe that is what is happening. Okay. Now what can we do? We can do the same thing, because I believe we have to do it, because if we don't do it, we would be underflowing the stack, as I just showed you. We can use uint 8 underscore t star ktop equals star k stack plus the size. Okay, we can use the size instead of using this here. We can use that definition inside the k main. Okay, we have the k top. Now we have to create the context, that is ctx, and it will be context star, and it's going to take k top minus size of context. Now we can use this space to actually build the context. Builds initial context, and it's going to take a context ctx, and it's going to take a void entry. Can't really, let's just define it here. Void user1 process1. It's not going to take anything. We can define it as x then, or we could just define it here. Int I equal to I1. We are just going to do this, and we need a semicolon, and we can also create the same thing again. And name it as process2. Process1 and process2 is just infinite loop with no thing. We can also use volatile, so we definitely just run this instruction If not, our fucking compiler will do random stuff to it. Okay. Okay, looks good. We can add that user process here. And then we have to add a stack, user stack. And user stack is just use stack. And now we can actually put t task context equal to ctx. That's good. But here, even here, we are right now storing it in top of the stack. We are storing the current tasks PCB not in its user stack but in its kernel stack. So I believe it is also a little bit good because the user process still cannot use it, but it is also local to the process because it's just being lying inside the kernel stack of that particular task. Or we could just use kmalloc here and allocate it and then use that for kernel build context. That is also fine. We'll just use this method. Now we can enqueue it, this task, into the scheduler. And we can call this twice. We say task, no, we say init task, and id will be 1, that means user process 1, and entry. Okay, we have it entry here, so we just give it here, and it is stack size, sticky size. Okay, that's the first one. We'll also have to fix it here because here we are passing it directly. We take it as an argument, so we could just give entry. And we can call it again to start another process, that is init task struct. Wait, just update it here. So we have created two processes. We'll just put it here. Nothing much. We have two processes, and we have the helpers, and that helper that is going to use kmalloc to allocate stuff, unlike the previous example where we have allocated things as static. We can use our kmalloc to do stuff like that. And what else? We still have to, we have everything already defined. If we can just go into our context.h and context schedule.c, where is this function defined? This builds context. It is inside scheduler schedule.c. Okay, and build context is not going to do much. It's going to set the SPEL1 0 pointer to the stack pointer, and we are going to set EL1 to entry. Wait a minute. What is ELR EL1 register? Bit confused. ELR EL1 register. Okay, it takes the address to return to. Okay, so because uh, because we will be inside kernel main after an exception is started, to return from the instruction interrupt handler back to user process, we need to store the return instruction somewhere, and that's why this ELR EL1 comes into play. And we store our entry as that. If we store our entry as that, okay, that means let's see, how do we actually start a program? Because initially we won't be inside a exception, right? So we are here, we task init, and then we set scheduler to current as T0. We enable interrupts, and we jump to first user enter. Okay, with a context. Okay, that's fine. That's fine. Still, what is first user enter does? If we get into that, it's going to restore an ERIT. Okay, we are doing this method. So to start an actual process, what we do is that we call a function, assembly level function, that literally just does what we would do if we were inside the interrupt context. Because if we are inside an interrupt context, we would come, we save the current context, we call the handler, and we just restore an ERIT. In this case, because we just updated our context and EL1 with the first function to run, we can just restore an ERIT. And if we go to restore an ERIT, you can see that EL1 is updated based on what we take from the context. And we also just load some registers, and boom, that is it. That is all we do. I think we can do the same thing inside our simple kernel. Where's my vectors that is? Okay, if I go into my vectors that is, I have the save context and restore context as it is. I also have the context and how it will be encoded in memory, or how it will be placed in the memory. Now I have to define this. I've defined it as a global variable, and it's already there. So I think that is also fine. Okay. That's fine. because I'm doing that ERIT, it will take that ELR1 value, which will be the user process, and it will load it, and next instruction that will be run will be within that user process 1, and it's just fine. Okay. Okay, what can we do now? We have almost everything inside our K-main. We just need to patch up a little more stuff. We have started it, and let's now we have initialized the process. Now we have to schedule T0 as the, currently it's saying T0. In that case, my task init is going to return a task struct. Okay, that's valid, because in this case we don't return anything. It's void because we define it outside, because we need the address to be valid. Its lifetime should be big enough. Sometimes because I have learned Rust, it feels, I mean, like I have better vocabulary to explain certain things in C++ too, because previously, before Rust, I would not have any way to explain why we have to put. I know, I mean, I would just say that address will live forever, but that's the whole point. Finding a lifetime of an variable is a key thing, because that is what the problem called use after free, because sometimes we free things and we don't free it is accidentally getting freed by someone else. That part of code does not know that this variable has to live as long as this lifetime, and someone else might be using it. That word is called lifetime. So this task has to live forever. That only then I can run multiple things, and I can always be sure that this variable is there and it won't be freed by anyone. And that is exactly what Rust's lifetimes are. So we have a way to actually see it, so we don't get confused. We know that, and a compiler root will directly throw an error if you try to free it somewhere else, because we know that someone else will actually holds it and they will clean it. We don't have to worry about it. We can just use it and move on. In my case, it would still be the same, because my everything is allocated in my heap. So those things will be there forever unless I actually go there and free it. So it would be a task struct. Now I can just pass task here. It's already a pointer, so it's just we don't have to reference it. We schedule it. Now we also have to start the what is it? Start the IRQs, or maybe enable IRQs, not start. and it is DIA of CLR 2. We are writing 2 into it, and then we start the first function. Task 1 context. We'll never reach here because as soon as we get into this, all it will do is just set eWritten, and eWritten is going to use the ELR1 value, and that will be the first user process. And as soon as we return into first user process, it has to finish, or it has to yield, and it has to give its CPU to the next process, and the scheduler will do that. And it's time to explain my scheduling algorithm that I have prepared the last time. So okay, so let's see what we have done here. Schedule on tick. This is what is gonna be called whenever there is a timer interrupt. It's not going to be called at every timer interrupt. As I explained it yesterday, if you go into my timer, this is the timer handler. That's my timer handler. That's my fucking timer handler. I guess I have to copy that part of code too. So I have my timer. In this code, I'm only initializing the timer. Timer is an actual physical device, so we need to initialize it, and we have to set the number of times to actually interrupt us. We are saying we want you to interrupt us after 1 millisecond. So after every 1 millisecond, we are gonna get a timer interrupt that's fired. Okay, that's fine. Now I guess I have to copy the handlers. I guess maybe that's what is this handler.c does. Let's open that and maybe we can write it so we will get a better understanding instead of just copying our old handler.c. Let's open it to the side, and in our side let's create a handler.c and class.c. Let's write it. My handler.c is just so fucking small. Where's my timer handler? Fuck me. Let's see. If we go into this, we have the start, we have the vectors, the context, we have the conlist.c, we have the k-main, schedule, we have the timer. And the timer does not have the timer handler in code. Why? We put it inside IRQ. Okay. We have the GIC. This is the actual thing I was talking about, because if we are throwing every instructions, every IRQs at our CPU, the CPU will never do actual work. It's going to be constantly be annoyed by interrupts. So only way to get some work done is by allowing someone else to handle the interrupts and pass certain interrupts into the CPU. I don't see that here too. What the fuck? Do I not need that timer handler? But without timer handler, how the fuck will we? Because if we go to interrupts, In interrupts, if we go to handlers, I have ELSync, ELSync, and if we go to timer, here I have IRQ handler. This is like a template code, so we have the IRQ handler. It's going to acknowledge interrupts, and it's going to check if it is a timer interrupt. If it is timer interrupt, then if we do this operation, we get 27. If it's 27, then it's IRQ timer IRQ, and then we pass it to timer handler, and timer handler is just going to increment a pointer, and once it is 1000. So I think currently we are not using it in our case, because I guess I use that for showcasing it as an example, because in our case, if we go into timer.c, all we do is that we set the frequency at which we need to be interrupted is 1 millisecond. So we are going to be interrupted only after 1 millisecond. So we are not getting interrupted at every clock high, because I remember this is a clock high, and our CPUs can do that billion times in a single second. So internally it is going to do the sampling, and it's only going to send the actual IRQ, timer IRQ, when it is 1 millisecond. That's the frequency. Okay, so we can enable it and do that part. That's fine. Okay. We have the timer handler code. Now we need the GIC code, because as I mentioned, GIC is the central part that's going to sit between all our external devices and the CPU and collects all of those interrupts. So let's copy that part of code. We can go back and see, and we are inside core. We don't need to be inside core. Do we have drivers? Okay, we have drivers, and we have a char. So we can add the IRQ driver. And if we can list that, it should be kernel simple scheduler, and it's drivers IRQ, and it only has GIC. Okay, it's desktop, host kernel, and it will be host kernel, and then it's kernel simple scheduler, and we have drivers, and we have IRQ, and we have GIC, and we can copy paste it here. It does not do anything else. It's the same thing. What it does is, if we go back to our kernel MMU and drivers IRQ and open it, it's more like UART. It's just going to initialize its base because it's a actual physical device. If it's a physical device, then then we need a memory mapped location, and 08000 is the actual location where QUMU maps this base. And there's two things. I guess that's how I remember it, because I also have wrote it. This is where every device will register their input. So this particular physical thing has two registers, because that's how we connect to external devices have registers, and those registers are memory mapped into that. And the GICD base is used by devices to register interrupts, and this is where CPU will. Okay, this is a register that is part of the CPU, because the CPU has to receive requests from GIC, and this is that particular register. Okay, so it's like let's draw a diagram. We have devices, and devices registers into GICD, and GICD will register into GICC, which is the CPU, and this is the flow. That's good. And it only has some few instructions. That's the initialization. Initialization is just enabling the base. So we write into that base vector 1, so we know that we have enabled GIC. And then we also enable timer for this interrupt. Every other interrupt will be ignored. Okay, we can also do this. So GICD base is currently only going to be listening for IRQ from timers. If we write to GICD base plus 1000 into this address, then it's the enabler register, and it's only going to take IRQ. That is the 27th bit, I guess. In this register, if we set the 27th bit, that means this GICD is only going to be listening for this IRQ. And then we have to enable GICC in CPU. It's the same thing. We take that register and we set it 1. And here we can also set some priority, I believe. So if we write to GICC base plus 4, this value, that is, I guess, 240, which is F0, maybe it's 11110, then we only get interrupted so it will only interrupt the critical ones. It will only interrupt the critical ones. Okay. This is the initialization code. It's pretty simple. As I just said, we just write to the base address to enable both the things, and we can also set to only listen for IRQs. I think this is not really necessary. It's just optional. And what does ACK means? ACK is just saying what is the reading from that register. So we have to read from that register to understand what is the current interrupt that has reached this GIC. So we go to the base plus C. This is where we read the current IRQ. And when we are done with the processing, we have to write to this address that particular IRQ saying that we are done with it. That we are done with it. And the read and write operation is just simple. We just dereference that address and we write to it. And we just dereference it. That's it. Nothing much. So it's a pretty simple code. And how do we use it? If we can come back to our timer example. I think this is where we have to go back to our main thing and see what we have achieved so far. I think we didn't achieve anything. We have only done some overall initializations. We have initialized tasks. We have scheduled them. We can also get into them, but and we have the timers ready, and timers are fired. Timers are fired. Timers are fired. So if a timer is fired, then we have to get into the vector table. Where's our vector table? This is our vector table. We would be reaching somewhere in this, probably IRQ entry or IRQ sync entry. I guess it would be IRQ entry. Sync entry means it would come from user space. And IRQ sync entry right now does not do anything. And this, I guess we have to register, write this code, this IRQ dispatcher. Because right now, I still have one doubt. We have the timer, we have initialized the timer, and where exactly are we passing the... Okay, GIC will automatically pass that timer interrupt to CPU. So CPU is just going to directly jump into exception mode, and it is going to come here. That is the somewhere here. That is just probably, I guess, this. And it's going to see this part, and it has IRQ dispatcher. And I don't even have an IRQ dispatcher. I'll probably have to write these three parts. Because this is the flow. We have the main CPU. No, the main K-main is running. Let's assume that K-main is running, and we get a timer interrupt. We have the timer interrupt code. We have initialized the timer registers. So we have to call them. Okay, we haven't yet called them inside our K-main. Yeah, we have to call the timer here, because if we call see, we have called the UART and we have initialized it. but we haven't yet called the timers here. That's the first thing. We have to call the timer interrupt here, and as per the flow, the k-main is running. Random timer interrupt is thrown, and it will be caught by GIC, and GIC is going to pass it to CPU. Now CPU will directly jump into the vector table. CPU will jump into the vector table. Where is our vector table? Fuck. Where's my fucking vector table? Yeah, it's here. So we jump into the vector table. Within the vector table, we have the ELR IRQ entry. Probably this is the one that will be invoked as soon as we invoke it. But this is my question. How will CPU know that IRQ EL IRQ entry is what needs to be executed when we get a timer interrupt? That's my question. I think we need to write something for that, because remember in my kernel interrupts code, we have driver IRQs, that is initializing GAC, and we have core, and we have a timer.c, and in that we have EL1 IRQ, and that is doing this X stuff. It's checking it, and we have a timer handler, and within that, oh, this is just timer handler. Do we really need it? First of all, why am I assuming I have to handle the timer interrupts? Timer interrupts can happen, but do I have to handle them? I don't know. What am I gonna do after I handle it? Within the handler, what exactly? Because in this example, I have handled it because I just wanted to show it with the print message that it is ticking. So we can, on every tick, we update the counter and we can put a print message. But what's the point of doing that in my current main scheduler? I guess let it be there. No, I need it. Because I need it because I just remembered it. My scheduler works based on that, because my scheduler has this. If you go into context, let's see. No, if we go into schedule.h, a task struct also has a time slice. What does that time slice mean? It's just ticks. So if I am running currently, and if the current tick is 1000, then I'm not supposed to keep running, because time slice should only be 1000. After that, I have to yield and give it to the next process. So I have to handle the ticks and drive myself. So that part should be done by my scheduler. So let's see the simple scheduler code and how am I doing it there. Inside vector table, I have see, in EL1 IRQ entry, what am I doing? I'm saving the context and I'm scheduling tick. So every time I get an IRQ, what I do, I'm just scheduling a tick and schedule on tick. What is schedule on tick? Schedule on tick is just this. If you go to core and scheduler and schedule.c, and it's this schedule on tick. It's just going to see this, and it's going to get the current context, and it's going to check if it's in running state. If it is in running state, if it will also check the slice left. It will keep on decrementing it in every tick, and if it is enough ticks and it's just 0, then we directly say that this is done, ticks are over for this, and we say it is ready to be scheduled, and we push it to back of the current. This is my logic. It's a round robin logic. So at every tick I'm going to be scheduled, and I'll check if the current process has enough ticks. If it has enough ticks, then it can run. If it doesn't have enough ticks, then I set its current state to ready, and I'll make the remaining slice left to 1000, that is back to its original value. And then I'll just go back. Okay, I'll also take the next I'll just pop from the linked list, and I'll set that to running. This is my logic. This is my entire scheduling. It's just going to check the current time slice. If it's there, it's fine. It will just return. The tick will return. So at every tick, I'll check the scheduler. I'll check if the current process can run or not. But one more thing. At every tick, this is also getting scheduled. But when will the actual work be done? The actual action will be done in that 1 millisecond, because remember, inside the timer.c, we actually said that this only needs to be interrupted us at 1 millisecond. 1 millisecond is a really long time within CPU. I guess within that we should at least get 50,000 or 60,000 highs. So within that moment we can actually run our process, and then after 1 millisecond we'll automatically fire this, and our schedule on tick will run, and it will do some it will check the current process if it has done enough work or not, and then it will reduce it, and it will keep on doing that. Oh my god, I'm just rediscovering my own code. I guess maybe I should have taken more documentation, but yeah, it's interesting. I have designed it that way so that on every tick, the actual scheduler is getting scheduled, and it's going to check the actual processes that is running, and it's going to either switch it or let it continue to run. I think it's good. This way we get the multitasking. That's it, I guess. Maybe we can implement it, but because this is a full-on theory session, I have done more theory this time too. Maybe I'll continue this next time. But in this session, we have setup stuff, that is to initialize the codes. So we have used our kmalloc to write the initialization of tasks, and we have also touched on the context part, how that works, and we have also explained our scheduler logic and how GIC works, and when our actual scheduler will get scheduled, because CPU is always running, and our process has to be running, and it has to be interrupted when the actual timer interrupt comes in, and the scheduler will load, and the scheduler will check the processes, and it will decide whether the current process has to continue or it can be killed. No, it can be yielded off, and a new process can get the CPU time, and the new process can run for some time, and after 1 milliseconds the scheduler will again get scheduled, and this thing keeps going on. That's good. That's amazing. I think that's it. I will implement the actual thing in the next session, because this is too much theory. Maybe let's just write down what we have done, we have initiated the tasks, we have started the scheduler code. What we have to we are yet to do is we have to set up what? Yeah, we have to set up the vector table. We have to set up the vector table with the schedule on tick. What else do we have to do? We have to test. Yeah, there's also one more thing. This is almost done in the previous examples. Now let's think about our case. In our case, we have to get interrupts from user space. Then we have to also set up the vector table with user space interrupts. So there will be multiple interrupts. We can be interrupted by the user process, and we need a handler for this that will check the syscall code. Okay, what else did we do? We have initialized. Let's just finish one thing before we leave, because that's important. That is just to call the timers, because we added it but we didn't call it here. Then it's this, because we have all this initialization here. Let's just call it in our k-main, so the timers will be running. It should be, I can just extend void, and we can call it in the top. As soon as we initialize the kernel, we can initialize the timers, and let's put a uart message. Maybe we can finish it off, at least a little bit of things. Timers are started. Okay, timers are started. What else do we have to start? We have to initialize GIC. Yeah. Okay, maybe only after initializing GIC we should initialize the timer. I think so. That's my GIC. It's here. And it should be just GIC init. If I go to timers, go to my, and put extend void, and I can init GIC. Init. I init the GIC, and then I start the timers, and then finally I also have to fix that part in my, okay, even my start is disabling the interrupts, so that's good. Now I can enable the interrupts in my k-main. Yeah, so this part should work fine, because I have in my start I have disabled it, and after all this work I'll enable it. So that part is also done. Is there any other like supporting templates that we have to initialize, so that in the next session we can actually write the handlers? What else do we have to write? That's why we need to write it down properly here. So we have to set up the vector table with the schedule untick, and then we have to set up the vector table with the user space interrupt handler interrupts, and then we need a handler that will check the syscall code. Okay, what else? Is there anything else that needs to be done? We have the user space. If we have the syscall interrupt handles, these parts should be fine. And if we write the actual handler, this part should be fine. And we have already written this part. I think this is all we need. Now we just have to finish up the vector tables and write the handler. Maybe in this session we can just finish up the vector tables part. What do I have to write in the vector table? I have the IRQ's entry that is going to dispatch IRQ, and I have the sync. I guess that is also done because last time I guess I copied this here. So these parts are also done. Now all I have to do is actually write these stuff. There's the IIQ dispatcher, syscall dispatcher, and I don't think I'm using schedule next anywhere. I guess the schedule next is supposed to be the we have IIQ dispatcher. Schedule next is supposed to be called inside IRQ dispatcher, because no matter what IRQ we get, it has to reach this IRQ dispatcher. In that, if it's a timer interrupt, then I call the schedule next, because in my previous example I did not do it that way. In my previous example I have done it like if no matter what interrupt we get, we are only calling schedule untick, but that's not how we want it in our kernel. So let's write that down. In our case, our finish IRQ dispatcher has to check the code of current IRQ and call the respective handler for it. Example, if it is 27, we call schedule ontick. In IIQ syscall, IIQ sync has to check if the code is a syscall, because if it is a syscall, then I guess it will be using SVC in ARM. So we know that we have to call the syscall handler. Is there any other possible reasons why we might be because if IRQ sync is always going to be called during a SVC, then we can just directly call the syscall dispatcher inside that. But I think let's just be flexible and also write a dispatcher for IRQ. So when IRQ is when we reach this IRQ sync, we get into a IRQ dispatcher. In that we check whether it is SVC. I guess maybe debuggers can also use this part. So yeah. So these are the things that we need to achieve, and that I guess we can write them the next time. Yes, That's good. Thank you guys. Next time I'll just implement these parts. Right now we have the structure that needs to be done, and we have also implemented a little bit of it. Yeah, we also have to test it, but once we done the entire implementation, we can test it, because that way we can get a full debugging session of the entire thing going on, and it'd be easier, because if I'm testing it one by one, it would be fast, but then I think that's not possible in this case, because we need the entire setup. Only then we can actually see if this whole thing is working or not, or at least even if this timer is working or not. Or if not, for everything I'll need to also write a small helper and dispatch it there and see if it's working, and then move on. That's just going to take extra time. Let's just write the entire template, and then finally do a full debugging session to see if it's working or not. Yeah, that's it. Thank you guys. Bye bye.